Okay, how's it going out there? This video I've titled Equations in Real Life and Function Notation. So let's say the learning targets. So first, to describe an equation or an inequality in words. So really, this whole video, I'm not going to ask you to solve any problems. I'm simply going to ask you to try to understand the grammar of mathematics. So I wrote there in parentheses, math grammar. This will all this we're going to talk about here is just going to be about like how do you read um, like a sentence in mathematics. And I find that students tend to if students are getting confused in a math class, it's often because they don't even understand what is being asked. Because learning to read the language takes a little bit of practice. Often it's also because it's not motivated very well. So I'm going to try here to motivate a lot of these things. The second learning target is using function notation to set up our equations and inequalities. Function notation is really like the analogy to like in grammar here, it's the analogy is to like punctuation. So you can't read a sentence very well without punctuation. Function notation is going to allow us to read and write mathematical sentences, equations, more easily. Okay, in particular, it'll help us with bullet point 3, identifying the variable to be solved for. And this final comment here is sort of a high level idea, but being able to plug in that skill that we've learned with functions is really like the opposite process or the complementary process to solving equations. So we'll see what I mean by that in a moment. So as a quick reminder, functions are like little machines, and these little machines are used to model patterns. And by pattern, what I really mean is like things that change, phenomena that change. And we've seen many examples of the types of patterns one studies in an algebra class. Um, but just as a quick reminder here, so when I say that a function is like a machine, what I mean is, imagine this little machine dude here is your function. That machine takes an input, so you push the little guy's buttons there. That's the input. Hopefully he's not ticklish. Oh God, I'm sorry for that. Anyway, moving on. You push the buttons and the machine gives you some output. It says bleep, bloop, bleep, and that is the output of the machine. Okay, so math functions really do work like this. You put something in and something comes out. That's what they are. They describe that. This is why they describe patterns. You might ask, how is this pattern changing at a given time? So you say to the machine, what does a pattern look like at time 1,000? And it says, here's what it looks like, right? So let's start with a little example here. So a function I'm calling rating of s, and now I'm using that function notation here. Okay, so let me explain. So the input to this function is going to be the name of a TV show. So the variable s stands for show. And the output to this function is going to be a rating. In other words, the number of stars that Mr. Bloomstein gives to that show. So you put something into this machine, you put the name of a TV show into this machine, and out comes the rating that I give that show. So that's written in function notation as rating of s. Remember, these parentheses tell you what the input is. So let's look at an example of plugging in. Here are some ratings I would give to some shows, and maybe you disagree. We can discuss later. Rating of Squid Games, I would say 1 star. I don't need any of that nonsense in my life. Rating of Stranger Things, again, rating is the function. Stranger Things is the input, and the output is 2 stars. So you can read it as like rating of Stranger Things equals 2 stars. Okay, and why do I give Stranger Things 2 stars? Well, it's basically just a cheap ripoff of every single like movie from the 80s. I'm just so bored of it. It's like, every Steven Spielberg movie and every Stephen King novel are just like what Stranger Things is now. So it's a complete ripoff. That's why I give it 2 stars. On the other hand, I'm a fan of the Great British Baking Show. It's a very pleasant, relaxing show about baking, and so I give it 5 stars. And this other show I've been watching recently, Only Murders in the Building, it's on Hulu. It has some comedy legends in it, Steve Martin and uh, Martin Short, and it also has Selena Gomez. So it's a really interesting mix-up of people in that show. Good show. I give it 5 stars. Okay, so this is plugging in. So I said earlier, solving an equation is like the opposite of plugging in. Okay. So here's an example of an equation with that rating function. So the equation now looks like rating of S equals 5. So what does this mean? This is saying we don't know, unlike when we plugged in, I'm not telling you what show. All we know here is that the rating is equal to 5. So when you're asked to solve this equation, so as I just said there, the input variable is unknown. In other words, the input variable is the show, the S, right? So I haven't given you a show. It's not like asking what rating does Mr. Bloomstein give this show. I'm asking you which shows do I rate as 5 stars? So you see the difference? I'm not plugging something into this, right? I'm not plugging a show in and getting a rating out. I'm asking which inputs give me this output of 5 stars. So which shows do I rate as 5 stars? Said another way, what do you plug in to get out a 5-star rating? See that? So this is the sense in which solving equations is the opposite of plugging in. Because you're not given something to plug in, you're asking what do I need to plug in to get a desired outcome. Okay. And just a quick note here, an equation may have many solutions. So in this last one, rating of S equals 5, there might be a lot of shows which I rate 5 stars. I showed 2 of them before. I have no idea how many shows I've seen that I would also rate 5 stars. Actually, incidentally, this reminds me, several years ago, Netflix actually offered a huge cash reward to anyone who could solve this equation accurately. I should have put that in the slides, but I didn't. I just thought of it now. So you could look it up. It was called the Netflix Prize. And if any mathematicians could come up with a very accurate solution to predict ratings, so like what would Mr. Bloomstein rate as 5 stars, they paid a lot of money for that. I kind of remember what happened. Anyway, that would be a topic for a different video. But needless to say, this sort of stuff is very practical. Netflix will pay a lot of money if you can tell them how to hook their audience, right? Like if there's an algorithm that says Mr. Bloomstein would love this show, so let's send that out to him so he keeps using our product, Netflix will pay. All right, so just quick summary again here, plugging in versus solving an equation, they're kind of two complementary sides here of the same idea. Plugging in, you know the input and you're trying to find the output, so you could ask me, plug in Game of Thrones, and what would the rating I give it? 3 stars. And solving an equation, it's the opposite. You know the output, but you're trying to find the input, right? So again, like that example, what shows do I rate as 5 stars? So you're trying to find the inputs that would give you that output. Okay. Here's another example. We have the variables T is the years since 2021. So T is time. C is the billions of tons of carbon emitted in the atmosphere per year. And C of T is a function here. So you might ask to solve the, you might be thinking about, if you care about climate science, solve the equation C of T equals 26. And so this equation in words is asking by what year, right? The unknown here is the T. That's the input we're looking for. Remember, we don't know the input with an equation. We're trying to find that input. By what year will the amount of carbon C equal 26 billion tons? So if you're wondering, this 26 is about half of what we currently emit per year. So you might ask the question, a good question to ask might be, well, when will we achieve half of that emissions if we project along the current sort of trends of how we're emitting? Okay, so this is an example of an equation you might care about solving in the real world. Okay, and you might say to yourself, why, well, Mr. Bloomstein, why did you write it like C of T equals 26 using this function notation and not just like C equals 26, right? Because sometimes you'll see in textbooks, they'll just say, take the variable and let it equal 26. So what's the difference between these two things? C still means carbon in each case. C means the billions of tons of carbon per year that are emitted. But what's the difference between the equation on the left and the equation on the right? Well, the one on the left uses function notation. Okay, and the one on the right doesn't. And really where this makes a difference is like the one on the left tells me what variable is being solved for. So in other words, it makes clear what question is being asked. On the left, I'm clearly asking you what time gives you this output. On the right, it's not clear what I'm asking for exactly, right? So it's just saying carbon equals 26. it's not saying as clearly like, okay, we need to solve for the variable of time, which is what the function notation does a really good job of showing, okay? So as an example, here's what I had in red there, C equals 10. Well, that says that there is 10 billion tons of carbon, because that's what C means, but it's not clear what's being asked to solve for. On the other hand, if B is the number of construction projects, say, per year, and I say C of B equals 10, now you can actually make some sense of it, because it's saying find the value of B, the number of construction projects, which contribute 10 billion tons of emissions of carbon, right? Or, for example, V might be the number of vehicles, right? How many vehicles lead to 10 billion tons of emissions would be captured by this equation, C of V equals 10. And so you see the difference between the yellow and the blue here and the red are the yellow and the blue, it's more clear what question is being asked just from reading the equation. C of V equals 10 means, okay, I know C equals 10, what values of V, the number of vehicles, would lead to a 10 here. And so you can see this is a very practical sort of thing, because in a real world example like this, there's tons and tons of input into, for example, this function, the carbon function, vehicles, construction, whatever. There's all sorts of things, agriculture, all sorts of things that contribute to the amount of carbon, and you might want to look at how these relationships play out, okay? So in summary, in the language of math, an equation describes a situation where two things are equal. Okay. The examples we looked at above had sort of the form f of x, so that's our function, x is the input, was equal to a number, right? And notice here that f of x is like a thing that changes, but the number is a thing that's constant. So like in the last examples we looked at, like c of v equals 10. So this was just some constant thing that's not changing. A lot of times it's also worthwhile to consider when two things which are both changing are equal to each other. So in this case, now I'm going to write an equation like f of x equals g of x. Okay, so that's two different functions or two different patterns, the f pattern and the g pattern. Both patterns depend on this variable x. And so you're going to ask, when are those two things f and g equal? In other words, what values of x make them both equal? So here's a simple example. Imagine that T is time. S is the supply of water in the Colorado River, which if you're watching this video from my Algebra 2 class or whatever class, your water, almost for sure, comes from the Colorado River, your drinking water at home. D is the demand for water in Colorado. Okay, S of T and D of T are both functions because the supply and the demand of water are things that change over time, right? So they both depend on the time. So if you're asked to solve the equation S of T equals D of T, you're asking when, or in other words, what values of T, the input, that you're solving for the input, will the supply equal the demand? And obviously this is a hugely important question for, in particular, the Colorado River, which is not in such good shape. It's experiencing a lot of drought. And so if you're a political scientist or you work for the government, this is a very important question. When will the supply equal the demand? In other words, when will the, will we have enough water for all the people living in Colorado? Okay. My last little comment here is that instead of asking when two things are exactly equal, you could also ask when one is larger than the other, and that's what's meant by inequality, right? Because they're now not equal, they're unequal or unequal, I guess, inequality. Okay, so that same example here, S of T, you might ask, when is the supply less than the demand? Or in other words, at what time T is the supply less than the demand? Because that's something you would really care about, right? If the supply being less than the demand means there's not enough water for the people in Colorado. And like equations, inequalities may have many solutions. Okay, so in summary, equation solving, you're trying to find the inputs which give a certain output. Okay, so it's the opposite of plugging in. Plugging in, you take the input and the little machine tells you the output. Okay, many real world problems, and we looked at a few, have the form, when will something happen? When will the supply of water equal the demand? When will the supply of water be less than the demand? All of those problems, you're solving an equation for time, for the input variable t. Okay. We looked at basically two types of examples. You looked at something like f of x equals 5. So again, the point of the function notation was that it showed clearly what variable is being solved for, in this case the x. So you're asking what values of x does the pattern f equal 5? And the second type of thing we looked at, you could have two quantities that are both changing, an f and a g. And now you might ask, when does pattern f equal pattern g? And in particular, using the function notation, you're looking for what values of the input t are the two patterns equal. So that's all I got, and thanks for listening.